Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Sometimes in business statistics we need to conduct a two-tail test instead of a one-tail test. A two-tail test has hypotheses that are a little bit different than the one-tail test. The hypotheses on a two-tail test would look something like this. Let's consider the employee satisfaction example that we just examined. The null hypothesis is that the average employee scores 56 on this satisfaction survey. In a two-tail test, the alternative hypothesis would not have a directional sign. That is, it would not say greater than or less than, but rather would have a not equal sign. From what point of view would management want to conduct a two-tail test in this particular example? Well, suppose instead of testing to determine if employee satisfaction had increased, management was merely testing to determine if employee satisfaction had changed in some way. That is, employee satisfaction may have increased, but it may have decreased. So if we draw a graph, for example, we still have the null hypothesis that a mean is 56 in the middle, but now because it's a two-tail test and non-directional, we have to consider the possibility that we might be rejecting the null hypothesis in either tail of the distribution. So we have two rejection regions and, if you will, two critical values. One thing about the two-tail test, however, compared to the one-tail test, the value of alpha is still the same. That is, if we were using an alpha value of 0.05 on a one-tail test, but decided instead to do a two-tail test, we don't get any additional alpha added to our mix. So therefore, in a two-tail test, we have to split the value of alpha. So in this particular case, we would have alpha over 2 of 0.025 in the upper tail and alpha over 2 equal 0.025 in the lower tail. How does this impact our testing and our result? Well, if you have 0.025 here, you have 0.4750 here, and of course, on the left side of the distribution. If you look these up in the standard normal z-table, you will find that the critical table value for this particular probability is plus or minus 1.96. So when we did the example as the one-tail test using an alpha of 0.05, our critical table value was z equal 1.645, and of course it was in the upper tail. You'll notice that our new critical values using a two-tail test with the same alpha value are larger. In other words, the critical values are further out. Our 1.645 fell, say, to about here, and our 1.96 is further out. So the impact of conducting a two-tail test versus a one-tail test in any given one same situation is that because we split the alpha in half, it makes it more difficult to reject the null hypothesis in any one tail of the distribution. In a one-tail test, our alternative hypothesis has a directional sign in it. For example, if we're testing that the mean is 56 in the one-tail test, the alternate hypothesis will either be greater than 56 or it will be less than 56. Of course, we pick one. In a two-tail test, our hypotheses are always equal and not equal. There is no directional sign allowing for the possibility that we reject the null hypothesis in either tail. In a one-tail test, we have a set value of alpha. Let's say alpha is 0.05. In the two-tail test, we also have a set value of alpha, but we must split the values of alpha because we have the possibility of rejection regions in either tail. So in any one particular tail, we only get half the value of alpha, resulting in a critical table value that in magnitude is larger than the table value obtained from the one-tail test, thereby making it more difficult to reject the null hypothesis in any one particular tail. So to summarize, conducting hypothesis tests about a single population mean, we use the z formula, z equal x bar minus mu over sigma divided by the square root of n. Then we learned that it's possible to conduct one-tailed tests or two-tailed tests. One-tailed tests have directional alternative hypotheses. Two-tailed tests have not equal in the alternative hypothesis. The result is that in a two-tailed test, the alpha value gets split, and the table values are, generally speaking, further out. The rejection regions are further away from the center of the distribution. In addition, with a one-tailed test, we use all the value of alpha in one rejection region, which is in one tail. In a two-tailed test, we take the value of alpha and split it in half because we have to share it between two tails. The result is that the critical table value for a two-tailed test is further out towards the rejection region than it is for a one-tailed test, making it harder to reject the null hypothesis. So let's remember, in hypothesis testing, in order to reach a conclusion, we will compare our observed z, which was calculated from the sample data, to a table critical z value, which is obtained using alpha for one tail or alpha over 2 for a two-tailed test. And lastly, let's remember to always interpret our statistical results in the light of good business decision making.